All right, here we go. Polygon notes. So we start with the definition of a polygon. A polygon is a closed plane figure. That just means it lies on a flat surface. A closed plane figure formed by three or more line segments. A closed plane figure formed by three or more line segments. So examples of polygons. Let's just start with the most simplest of polygons, a triangle. In this case, I've got the sides as this kind of dark maroon color. The side is just a segment. The points where the sides meet, the end points of those segments, are what we call vertices. So the sides are the segments and the vertices are the end points of those segments, where two segments meet. Now later we'll look at what the names of these different polygons are and what you're going to be responsible for knowing. Congruent polygons, notice this is one that you've got to have memorized, hence the little stars. So congruent polygons have two requirements. Their corresponding sides are congruent and that's an important one, which is why I've got it in uppercase letters, corresponding angles are congruent. All that means is that the sides in one shape are going to be congruent or the same length as the sides in another shape. And the angles in one shape are the same as the angles in the second shape. So let's draw ourselves a polygon here. Make that a darker color than pink. All right, 1, 2, 3, 4. So here I've got a four-sided polygon, and I'm just gonna, whoa, try that again. I hit the wrong thing, sorry. All right, I want to copy that, and I'm gonna paste it over here so that I have a second copy of it, like so. Now, in terms of what we mean by corresponding sides, each side in this first shape corresponds or has a side in the second shape that is the same length. Likewise here, these two would be congruent. And notice that each pair gets a different number of tick marks. And then the last side, 4 of them. Now, it doesn't matter in this last shape which direction it's turned. Let's solve that problem for just a second. Hey, there we go. So here, if I turn this shape, the corresponding sides are still congruent, regardless of the fact that the direction has changed. Okay? Likewise, not only are corresponding sides congruent, but corresponding angles are congruent as well. So each angle here corresponds to an angle there. 2 marks here, 2 marks there. 1, 2, 3. That one's kind of squished. And then this one I'm going to mark a little differently, like so. But we still indicate that there are 4 pairs of congruent sides and 4 pairs of congruent angles. Now, whenever we talk about congruent polygons, we need names for them. And we name a polygon by starting at one corner and working our way around it. Okay, so in this case, I have polygon A, B, C, D. And we name the capital letters that are the vertices, is congruent to, and I have to make sure that I name the other one in the same order. So where here angle A has 3 congruent marks in the other polygon, I want to start with the angle that also has 3 congruent marks, and that would be E. Angle B is listed second, and that's the one here with the mark and the tick mark through it. F corresponds to that. And then we could do the same thing for C and D, and we end up with E, F, G, and H. Let's clear that up a bit. And remember, this was corner F here. Okay, so you name one polygon. It doesn't matter which order you name them in for the first one, but the corresponding parts must be in the same position in the second polygon. All right, so in this next little bit, we're going to review the names of different types of polygons. I expect that a lot of these are going to be review for you, so I'm not going to spend too much time describing them, but 3 should be a triangle. 4, quadrilateral. Typically, I'll see people put something like rectangle or square. Those are examples of quadrilaterals. That's not the general name. 5 is a pentagon. 6, hexagon. These are names that you will need to know. 7, there are 2 answers. You could either give heptagon with an H, or you could do septagon with an S. Either one is acceptable. I tend to go with heptagon, but that's just a matter of choice. 8, octagon. 9, nonagon. Now here, this one might be a little less familiar. Non as in 9. 10, decagon, like deca means decade. 11 and 12 are going to be your new ones, most likely. Undecagon. Now, if you look at your prefixes here, you'll see what they mean. Un, like uno, meaning 1. Deca, meaning 10. So 1 and 10 make 11. Continuing on with 12, dodecagon. And there again, the prefixes tell you the name. Do meaning 2, like think dose. And deca meaning 10. So 2 and 10 make 12. Hence why it's called a dodecagon. Now anything beyond 12 sides we refer to as an n-gon, where n is the number of sides. So something with 14 sides would be a 14-gon, and a 15-gon, and a 16-gon, and so forth. Okay, these last 3. The first 2 I think you probably already know. An equilateral polygon is a polygon with all of its sides congruent. A polygon with all of its sides congruent. Gee, it looks a little funny there. All right, so we start with a polygon. I'm just going to use a simple equilateral triangle, 3 congruent sides. Equiangular polygon is very similar, except instead of sides, we're talking about angles. So a polygon with all of its angles congruent. And there again, I'm going to go back to my lovely triangle. 1, 2, 3 congruent angles. So equilateral and equiangular, fairly obvious which one's which. A regular polygon is a polygon that is equilateral and equiangular. So in this case, we go back to our 3 equal sides, 1, 2, 3, and 3 congruent angles, 1, 2, 3. So equilateral, all sides are congruent. Equiangular, all angles are congruent. And regular is both equilateral and equiangular. All right, moving on to the next page. A diagonal of a polygon. Now, we know what a polygon is. The diagonal Most polygons have, or all polygons have, at least 2 diagonals. But a diagonal is a segment that joins two non-consecutive, we'll talk about what that means in just a second, non-consecutive vertices of a polygon. Okay, so I'm going to start with a pentagon. So I want a 5-sided polygon here. 1, 2, 3, 4, 5. All right. Now, in terms of what a diagonal does, a diagonal, remember, is a segment. So we're going to start with our segment tool here, and it has to join 2 vertices. This vertex here at this corner and this vertex are already connected. That's a side. So that would not make this green segment a diagonal. It would make it a side. To be a diagonal, it has to connect 2 vertices that aren't already connected by a side. So this would be one example of a diagonal. I could do another diagonal from that same point down to this point because they aren't already connected. So it's connecting 2 vertices that aren't already connected, that aren't a side. So here there are others that I could draw. These are the 2 possible ones coming out of that corner. I could also draw from this corner down 1, 2, another one here, and that would be all of them in that particular in the pentagon. And that's where we get our lovely little star. Okay, so in our example over on the right, draw all possible diagonals from one vertex of a convex heptagon. We'll talk about what convex means in a minute, but we're just going to start with a 7-sided figure, a heptagon. I'm going to show you how you can easily draw a 7-sided figure. Okay, so the trick is start with a circle. It doesn't have to be a perfect circle, but start with a circle. And on that circle, draw as many points as you would need vertices. So here I'm looking for a heptagon. I went 7 points. So I'm going to draw 7 little dots. And you can space them out evenly if you want. You don't have to. But draw 7. 1, 2, 3, 4, 5, 6, 7. 7 dots along that circle. And then we're going to connect those dots with our straight line segments. So get your straight edge out and just connect the dots. And you're going to work your way around the circle, just connecting dots to get that heptagon. And you can do this method for any convex polygon. Like I said, we'll talk about down here in this next bit what makes it convex or concave. Now, questions with diagonals will involve one of 2 things. They'll either, like this one, say draw all the diagonals from one vertex, or they'll say draw all the diagonals of the polygon. So in this case, I want to pick one of my points. Doesn't matter which one you choose. I'm going to choose this one right here. And I want to draw all of the diagonals that extend from that vertex. So here, remember, you don't want them to be already connected. So 1, starting back at that same vertex, 2, 3, 4. Now remember, I can't connect these 2 along this side because that's already a side of the polygon, and I can't connect it to that one because that's already a side of the polygon. So in this case, there should be 4 possible diagonals coming from that single vertex. All right, so let's talk about what makes a polygon convex and what makes it not convex or concave. A convex polygon has no line scratch that has no line containing a side passes through the interior. Passes through, oh, I'm running out of room. The interior. So let's look at some examples of shapes, and I'll show you what that means. Okay, so let's start first with our lovely rectangle. And then I want to look at a pentagon. And lastly, let's talk about a hexagon. Okay, so each of these shapes has an interior and an exterior. Interior, I'm going to color the interior of that one green, and the interior of this one, and the interior of that one. So the interior is all the points inside the shape, contained inside that closed shape. Now if I were to take each of these sides and make them lines, so here if I make a line straight along that side, and I make a line straight along, whoops, I missed, straight along that side. Notice how it never goes inside, it never gets into the green, it's just passing right along the side of that shape. That makes this one convex, because none of those lines go into the green area. And I could do the same thing here with the pentagon and draw all of those sides, and I'll see that none of them go into the green area as well. Likewise, the hexagon would have the same outcome, and that's what makes it convex. So what's the difference between that and concave? A concave polygon is simply a non-convex polygon. In other words, it's one that the lines do cross into the interior. And a really easy example of that would be a star. And I'll show you some other examples in just a second. So here again, let's color the interior of the shape green. And if I start to draw a line along one of the sides, for example here, not terribly straight, but if I draw a line through there, we can see where right here it passes through the interior of that shape. And that's what makes it concave. Now some people would describe a concave polygon as one in which one vertex kind of falls in toward the interior of the shape. So another example, 1, 2, 3, 4. Shade that interior. And there again, if we try to extend, some of the sides will work. Like if I extend this one, it's just fine. That's not a problem at all. But when I go to extend one of these two, I can see where it crosses through the interior right here, and that's what makes it concave. The next several examples ask you to draw an example of each of the following. Whether it be convex or concave, it also gives you some that refer to regular. We refer to triangles and quadrilaterals, pentagons, etc. At this point, I want you to pause the video, and I want you to work through the 10 or so problems that are there, 12 problems. And when you think that everybody's done, then start it back up again and see if your answers were correct. So pause the video right now. All right, so a convex octagon. So when it's convex, I start with my circle. I'm going to start with a circle on all of them. In this case, I want an octagon, so I'm going to add 8 points along there. You can space them out evenly if you'd like, but you don't have to. So convex, all the points lie on the circle. Connect the dots, and you're done. 1, 2, 3, 4, 5, 6, 7, 8. And there's the answer to number 1. All right, on to the second one. Draw an example of a convex regular pentagon. Now regular, remember, means that all the sides and all the angles have to be the same measure. So that means when I go to draw my points, I'm going to space them out as evenly as I possibly can. This should look like home plate on a baseball field. So connect the dots. Get all the right color here. 1, 2, 3, 4, 5. Number 3, draw an example of a convex equilateral quadrilateral. Easiest way to describe that is a square. Equilateral quadrilateral. We could do a square. We could also do a rhombus, which is a square that looks like it's kind of been shoved over, slightly leaning to the side, but all the sides are the same length. 4, draw an example of a concave decagon. So I'm going to start with my circle the same way I did before. That gives me the general placement of where my vertices will be. Now here, for a decagon, I need 10 points. But to make it concave, I want to make at least one of those points in the interior. So 1, 2, 3, 4, 5, 6, 7, 8. Where do I want to put them? I'm going to erase one here and space them out a little differently. 9. It's just a matter of, it doesn't have to be regular, so we're okay to put them in whatever. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, now that I've got all my points, whenever I go to connect them, at some point I need to jut in here toward the center. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10-sided figure that is concave. So convex, put all the points on the circle. Concave, put at least one of them on the inside. You can do 1, you can do 2, you can do however many, as long as some of the points are along the circle and some of them are inside. Draw an example of a concave hexagon. So there again, we're going to start with our circle. Put some points along the edge of it. I need 6 of them this time, and there again I want it to be, let's see, at least some along the outside and some on the inside. Now here I'm going to put more than one on the interior of the polygon, but you can do whatever number. Whoops, didn't change my color, but that's okay. 6 segments. So that's also one possibility. There are multiple answers to a lot of these. There's nothing that says you have to have it one way or another. All right, moving on to the last page. 6, draw all of the diagonals from one vertex of a convex octagon. So we're going to start with our octagon. I'm going to cheat a bit for the sake of time and just draw an octagon here. All of the diagonals from one vertex. So we start at one vertex and draw all of them from that point, just like what we did earlier. So I'm going to start here. 1, 2, 3, 4, 5. So we should have 5 of them on number 6. 7, how many distinct diagonals can be drawn, sorry about that, can be drawn from one vertex of a convex nonagon? Okay, so I need a nonagon. So I'm going to start with my circle, like I've done before. Put 9 points along its edge. 1, 2, 3, 4, 5, 6, 7, 8, 9. Connect the dots. 1, 2, 3, 4, 5, 6, 7, 8, 9. And here we want to draw all of them from one vertex. So we start with our straight edge in our segment. I'm going to start down here on this bottom corner. 1, 2, 3, 4. Remember, diagonals connect vertices that aren't sides, that aren't already connected by sides. So in that case, we get 6 different diagonals. And to answer the question, how many distinct diagonals do we get? 6. Draw all of the diagonals of a convex pentagon. Note it says all of the diagonals, so we start with our pentagon. And we draw all of the diagonals that are possible. So, whoops, 1, 2, and that's all from one vertex. So we go to here, there ought to be 2 from each vertex, since that's how many we got from the first one. Here at this vertex, I've already got 1 drawn. Now just to check, there are 2 there, 2 here on the right, 2 on the bottom right, 2 on the bottom left, 2 over here. So in that case, all of the diagonals, that's where we get our star. Draw all of the diagonals of a convex decagon. Excuse me. So we're going to start with a decagon. Whoops. Wrong shape. Let's try that again. Well, goodness. What is going on? One more time. Hey, there we go. Now it's working. Decagon. So 10 points. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. All right, make sure I got all 10. Yep. Draw in our segments. Connecting the dots, always a fun little game. The only reason I do the circle trick is because I find that sometimes people, especially with ones like 7 sides and 9 sides and 11 sides, kind of get to a point where they're like, I can't get them all. So if you do the circle with the 7 or 11 or however many points you need, it kind of gives you a starting place before you start drawing the segments. Start with the vertices first and then play connect the dots. So all of the diagonals. So let's start with doing the diagonals from one vertex and see how many there are from each vertex. So here I get 1, 2, 3, 4, 5, and 6, and 7. So I ought to have 7 coming out of every vertex. So I'm going to start at this next one on the right. 1, 2, 3, 4, 5, 6. There it is. I missed that one right up there at the top. 7. Go to the next vertex. There's already 1 coming out of there. So I need to add 6 more. 2, 3, 4, 5, 6, 7. Remember, you should have 7 coming out of every one. Going to the next point, I already have 2. I have to add 5 more. 1, 2, 3, 4, 5. This one already has 3, so I need 4 more. 1, 2, 3, 4. That one already has 4, so there are only 3 to add. 3. This one has 5, so I need 6 and 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And there we go. We've got them all done. Lovely little cobweb. Now, if your original vertices, the points along the circle, if they're evenly spaced out, you should see a nice symmetry there in the interior where all those diagonals are intersecting. Mine's fairly symmetric. Not perfect by any means, but fairly so. All right, last 3. Sometimes, always, never, and true-false questions. So number 10, a regular hexagon is congruent to a regular octagon. Well, they're both regular, so does that make them congruent? No, because a hexagon has 6 sides and an octagon has 8 sides. Remember, the definition of congruent polygons says that each side in one shape has to have a corresponding side in the other shape. So here, 6 sides in the first shape cannot possibly correspond to 8 sides in the other shape, so this will be never. 11, true or false, an equilateral triangle is always regular. So the question is, remember what regular means? It's both equilateral and equiangular. So is an equilateral triangle always equiangular? Yes, so that's true. And the last one, a point can belong to the interior of a polygon and the exterior of a polygon. And that would be false. You can't have a point that's both inside and outside a shape. That'd be like saying you have some city that's part of both the United States and Canada at the same time, but it doesn't lie on the border. Because notice it doesn't say on the shape, it says inside or outside. So false in that case. All right, so that takes care of your polygon notes. Homework for today was out of the book. Should have been given that in class.